Right, so momentum. Well, first of all, what is it? We know from everyday language that if something big and heavy is moving towards us, we can say it's got a lot of momentum. If it's moving faster, it's got more momentum, right? So a speeding train would have a lot more momentum than a ping pong ball being hit by a little table tennis racket bat. So it's you can think about it as a measure of how difficult it is to slow something down or how difficult it is to stop something. In actual fact, the force to change, if you wanted to change the momentum of something, then the force is going to equal to the change in momentum divided by the change in time. So the rate of change in momentum is what is equal to the force. That is actually one of Newton's laws. The one that F equals ma that you've learned about before was originally actually defined as this, and this can lead to F equals ma. But we'll leave that for another lesson. The conservation of momentum is where this topic gets tricky, and and really where all the practice needs to be. Like, what is momentum? How to calculate it? Oh, I missed that bit on the video just now. Is momentum is equal to mass times velocity, but the conservation of momentum is where it gets hard. So what it means is the total momentum before and after an event, something occurring, is going to be the same as long as we consider all the variables. So let's imagine we have something, this 3 kilogram ball moving towards this 1 kilogram ball at 5 meters per second. The total momentum before is going to be equal to the total momentum afterwards. Let's say that afterwards they stick together and then move off at some mystery velocity. So the total momentum before is equal to 3 kilograms times 5 for this one, plus 1 kilogram times 0 for that one. So this is just going to be 0. The momentum of something not moving is 0. No surprise there. And so the total momentum is just 15, and the unit is kilograms meters per second. So because of the conservation of momentum, that's going to be the same afterwards. And again, it's equal to mass times velocity. This times the mass is 4 kilograms because I've added them. We add them together, and then we multiply it by the velocity v. So to find the mystery velocity, we rearrange the equation 15 over 4, and that's equal to 3.75. So you've got, so when I say an event, like I said, it's not just a collision, but it could be a collision or an explosion. So let's think about what an explosion is. Let's say we've got two objects, and they are touching one another, and then and then after, it doesn't have to be two, it could be more than two, and then after a short moment, they are moving away from each other, right? This is an explosion. If you think about it, that's also what happens in an explosion. We have something sitting still, and then after the explosion, everything, different parts of that something is moving in opposite directions. The explosions are a bit weird to get your head around to start off with, but once you get the hang of it, they're actually much easier to calculate and work out than collisions. But we will look at that late in a moment. Just briefly about the collisions, and what do we need to know? Well, we can think about them all as one. Just basically apply this rule, and then you can just, doesn't really matter. But it's still good to just be familiar with the different types of collisions and what could occur. So you could have one object moving and one stationary, like I've got here. That's the simpler type. We could have both objects moving towards each other. That's when you would have to work out momentum of both objects and add them together to work out the total momentum. We have one object catches up with the other, right? Now, and then also, by the way, after the collision, they could stick together like we've got here, or they could bounce off each other. Now, one other thing that did occur to me, the important thing that we want to realize is that velocity is a vector, and so momentum is not mass times speed, it's mass times velocity. In other words, momentum is therefore also a vector. So what will happen in some of these some of these questions that we're going to do is we will do the sum and we will find we get a negative answer, and what that tells us is it's going the opposite direction. As the opposite direction to what? Well, whenever we are working with forwards and backwards, we're working with velocity, with vectors, we're always indirectly, without thinking about it, deciding what is forwards, as it were. In this case, forwards is to the right, because I've not called that -5. I've called it just 5. And because I've called it 5, then that means forwards is to the right. So if I did a bunch of sums and I got some of this velocity is negative, it would tell me that the velocity is moving to the left. And you're not going to get that in this case. There's no reason that this would go towards that. They stick together and they'd bounce, they'd move off to the left. But let's say they didn't stick together and this was very heavy. Then let's say we have, like, I don't know, a 1 kilogram mass hitting a 100 kilogram mass. The 1 kilogram mass you would expect would bounce off and move to the left. But there might be a point at which it doesn't bounce off, but it moves ahead. Anyway, that can be worked out using the conservation of momentum. All right, I'll stop the video there and we'll do some practice.